Okay, so we did an exponential growth model. So it makes sense that we should also cover a logistics growth model. So basically, if you did one growth model, you should be fine doing the other. So let's kind of like ease ourselves into it. Hey, we did growth models before. So we had a lot of information in our Do Now that started talking about population growth and how its relative growth rate, and it's positive, but it can decrease as the population increases due to environmental factors. So there's a maximum population, M, and a carrying capacity, where the relative growth rate is proportional to 1 minus P over M. So that's actually something we see here, even though we copied that into Do Now. With a positive proportionality constant, K, and there we see K. There it is. Here it is. Here it is. There it is again. Yay. Which is part of the logistics differential equation. So here we've got it. The logistics differential equation can be written either way, this way or that way. And our relative growth rate is expressed here. And we know our exponential differential equation. Okay, so this is kind of just review. You should be familiar. If you're not, that's okay. Just look it over. It looks something like we've done before. All right, so these are just the forms that we see for our exponential differential equation and our logistics differential equation. And we're putting out, hey, there's a relative growth rate. All right, so what can we do? We can tackle our example problems. So let's do example 1. So in example 1, okay, and please write this down. You can pause and copy it down. I'm just going to kind of go ahead and start example 1. Why isn't this writing? There it is. A population has a logistics growth with K is equal to 0.05, M is equal to 200, and P of 0 is 10. A, write a differential equation. B, find a formula for P in terms of T. All right, so we have a lot of our information here, and we're going to apply it to our formula. The formula that we're going to use is this one here, because we have P and K and M. And it's asking for a differential equation, and that's usually dP over dt, so that's why I'm going to use this one, okay? Not that one, because there's no carrying capacity. So here we go. dP over dt is our given information, and we're going to leave it in terms of P, because that's what we need. We need it in terms of P. And so here we have it. dP over dt will simplify to be P over 4,000, once we simplify that fraction, times our quantity 200 minus B. And that's part A. Part B, find a formula for P in terms of T. So this is where we have to solve our differential equation, okay? And so when we solve our differential equation, we're going to have to take everything that's in terms of P and put it on the other side of our equals and leave everything like a constant or anything in terms of T on the other side. So this actually implies here that we need to do a little bit of partial fraction decompositions. So I'm going to post a video from my pre-calc class that reviews partial fraction decompositions, where you have distinct linear factors, such as these. So that way you know how we're creating our fractions for this side of the equation, okay? I am going to show the work, but in order to do that, I need some space, so I'm going to erase some of this. Hopefully you get up to this part. Okay, so that got a little sloppy when I was writing it out. So basically it's a decomposition. I broke up this fraction into two others. That's 200p in the denominator, and in the parentheses there is another 200 minus p. That looks a little bit like an 8 in there. It's a 0, and then that's p. Okay, so this is actually what we need to split up our fraction on the left side of our differential equation. Okay, so what we have is 1 over 200p and 1 over 200 minus p is equal to 1 over 4,000 dt. Whoops, I missed my dp over p. Okay. Whoa, that got really, really sloppy. I didn't intentionally mean to do that. Okay, I was just trying to squeeze that in. Hopefully you can see it. So we're going to integrate both sides of our equation. Okay, this has like a dp here. It's right on top of the equals. Okay, so that means that I'm going to integrate our first fraction with respect to p, and I'm going to integrate my second fraction here. Oh my goodness gracious. These 200s are killing me. Well, not literally. That's okay. They're just bothering me because it's becoming so sloppy. And I can take out the constant. Don't forget, you can take out constants. Okay, and thank goodness we can easily see how this we can integrate. Yay! That's 1 over 4,000 t plus c. This side we need a little bit more work. Okay, so I'm going to rewrite that and do some work with this. Okay, so let me erase this and start working on the left side of our equation. Okay, so as I was saying, we integrated left side, and now I kind of straightened up the left-hand side. Okay, we integrated the right-hand side, and I straightened out the left-hand side. So you can see over here that this is 1 over 200 ln, absolute value of p. But over here, we may need some u substitution. And with that being said, it's not the ln of 200 minus p. Okay, be careful, because du is negative dp. All right? So when we're integrating, here we get a negative 1 over 200 ln, absolute value of 200 minus p. All right, this stays the same. You can just kind of bring that down. And since 1 over 200 is visible in both parts of our equation here, on the left side of our equation, we can actually factor that. I'm going to take out the negative only because I like to work with positive numbers. But that would leave me with a negative ln absolute value of p. That's okay. There are log functions, so I can combine these two expressions together. Again, I'm just bringing down the right-hand side. So over here, okay, it becomes combining the log expressions, ln absolute value of 200 minus p over p. Okay, So remember to review your properties of logs. Again, I'm just bringing down that side of the equation. But because I have the negative 1 over 200, I can multiply by negative 200 on both sides. Okay, that will help me get e to the ln of the expression. Okay, and we will do that in one moment. Let me actually do what I said. All right, that would make this side negative 0.05t plus c. Okay, if I carry this fraction over to the right side of my equation. Now I'm going to use e on both sides. This will eliminate, and so I end up getting you to copy this. Make sure you copy that last one because I need to erase and continue from here. Okay, so that will leave us with our beautiful fraction and ce to negative 0.05t. Okay. At this point, you're probably like, oh my God, example 1 is so long. Oh my goodness. All right, I'm sorry about that, but we can now plug in the values that they gave us. And it took a while, but p is 10 and t is 0. So by plugging that in, we can solve and find c is 19. So 200 minus p over p is 19 e to negative 0.05t. And from there, we can solve for p. We can take a few more steps than I just took here by cross multiply, combine like terms, and this is our formula for p in terms of t. Okay, I know that it took some time, but that's okay. We're up to example 2, all right? And notice the format of this answer. It's not over here. It's not exactly the same thing. They do have that same looking format when it is a logistics growth model. Okay, this actually is part of example 2. So, example 2 says the number of students infected by measles in a certain school is given by the formula above, where t is the number of days after students are first exposed to an infected student. Okay, this is similar to a pre-calculus question that I know I've done before. So you have seen probably these equations before, and you've used them as functions, but never as actually finding them, and you need calculus to actually do that. So congratulations if you did that in example 1, and let's continue with example 2. Okay. Let me cross this out. We did example 1. So example 2, A, it says show that the function is a solution of a logistics differential equation. Identify K and the carrying capacity. B, estimate P of 0. Okay, so we have a few things that are being asked of us here. And in example 2, part A, it's not in the forms to see K, to actually view it. So we're going to need some work to do here. All right, so I'm going to go through. The K we can see is actually the absolute value of -1. It is 1. And our carrying capacity is our numerator of 200. So our carrying capacity for the last problem was also 200. So it's kind of in that format. We just are not used to seeing it in the forms that I gave you. Okay, so I just wanted to go over that with you. So kind of keep that in mind. Okay, let me point that out. So 200 is M, and the K is the coefficient for T, but it's got to be the absolute value. Okay? All right, so that was part A. Part B. Okay, so this one's kind of easy. we just need to plug in 0. And this is very similar to what we had to do in the last one with substitution. And if we plug in 0, we get approximately 0.993. So we do need the calculator for this. So what is being explained from this is that when T is 0, so initially there was 1 student, the first student infected. With the measles. And then if you were to find P of 5, okay, it will show you what the population is after, when T is 5 and after 5 days, okay, or you can make it 7, so you can find out how many were infected with measles after a week. So you can actually see how it grows, and you get an idea for other application problems. All right, so good luck, and let's do some practice.